All right, I'm not going to talk through the answers very much in section 4.1, just having you check. We'll go over questions in just a second if you have them. Meanwhile, let me update your backboard because it needs some updating. Be up to date, right? As in homework showing up when they're supposed to show up, et cetera, et cetera. Okay. And homework number, what is this homework number? 23? Is that 4-1? Okay. Okay. 2B test. Let me scroll down. So you guys have had more than enough time on 2 and 6 and 12. Number 16, sample answers. What? Why sample answers? What are they asking for in the directions of 16? Starts, oh, complement and supplement? I thought it was complementary. Or, sorry, coterminal. Yeah, coterminal makes more sense because complement, supplement, there's either one answer or no answer, right? Got it. Got it. One answer or no answer. But for coterminal, why could they say sample answers and it's not just one or two definite answers? You can go around and around and around and around. So if you wanted to be little stinkers, you could have been like, I'm going to add 24 pi. Sure, you could have added 24 pi and landed back on the same angle because how do I know adding 24 pi lands you right back where you started? If you have any angle, adding 24 pi would get you right back to where you started. Why? It's a full, right, it's a multiple, I would say, of 2 pi. Why would 17 pi not work? You would end up on the opposite side. Because it's an odd, right? It's an odd multiple. So it would be a multiple of a single pi. Or I should say an odd pi. Yeah, Tony. Oh, yeah, go ahead. When you're done, you can just put it on my desk. So could you have added 2 pi? Sure. Could you have added 24 pi? Sure. You would have been fine. Or any other even multiple of pi. But for, I think they said they wanted a positive and a negative, so you had to somehow subtract. You could have subtracted 2 pi, you could have subtracted 24 pi, you could have subtracted any even multiple of pi, and you would have been right. Okay? Guys, what's the easiest way when you have a fraction and a whole number, put them together? Go 2 2/3 and then change the mixed number to an improper fraction? Maybe. What do I like better? Because I'm trying to teach you to think naturally in radians, which means you need to be able to do fractions. I would change 2 pi, 2 calzones, to being cut into thirds and asking how many pieces. Well, if 2 whole calzones got cut into pieces, is that? Oh dear. Oh dear, if you're in a pizza restaurant, 2 calzones come. You cut them. What do you have?
6.
Kyle knows the answer. So you're in a restaurant. Close your eyes. Don't fall asleep on me. Some of you are spacing out, and I don't know what you're looking at or what you're doing right now. Close your eyes. You're in a pizza restaurant. They have like the red checker tablecloths, right? The bread has come. Maybe it has like some sort of like garlic something, 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 something. Maybe you have like a macaroni grill, balsamic, and olive oil, something, something, something. Anyway, the bread's come. Okay? You get your calzones. Calzones folded pizzas. Big old pizza pockets, but nicer because they're semicircular. Okay, come back. 2 whole calzones are on the table. You slice it into thirds because they let you slice your own calzone. I don't know. How many slices are in front of you? How many? 6. How many? 6. Okay, so why don't we answer when I ask questions? Awkward. Goodness gracious. Okay. Coming back. So how many slices? 6. So take 6 and add 2 and you have 8. Dun, 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 dun. Anytime you have a whole number, just think, what do I want it sliced into? Thirds. What do I want it sliced into? Fourths. So there's going to be 8 slices. 8 minus 9 is negative pi. Why am I telling you this? Because I want you to do radians like this. So if I was to ask you something like, I know it's probably in homework somewhere, but I'm just going for it. The supplement, ooh, you have to know what a supplement is. The supplement of pi over 6. Supplement angles add up to be what? Good, in radians. Pi. So a whole calzone. How much more do I need if I have this and I want to go up to a whole calzone? Yeah, just think, slices. There's 6 whole slices. I have 1. How many more do you need? 5. You could do this whole like, oh, I have to do pi minus pi over 6. I hate fractions. Let me complain for a little bit. And then I need to go ahead and combine. But I can't combine until I have a common denominator. It's so much easier to think of 1 whole pi is 6 slices and 6 minus 1 is 5, right? So anytime you have a whole number, you can always just make it pi. It could be, it depends on what you slice it. 5 over 5, 4 over 4, 6 over 6, 3 over 3. It can be whatever you want it to be. Same with 2 pi. Except this one's going to be 6 over 3 or 8 over 4 over 6. That's how you think in radians, is you don't get stuck in the whole number thingamabob. Okay, think in slices. Moving on. Why am I holding all this stuff? Anyway, that was number 16. Shoop, 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 shoop. Did you guys graph correctly? Negative 30 degrees. They let you do degrees for a little bit. Spoiled, rotten. Negative 30 degrees. And negative 750 degrees. Both equivalents of going positively 330 degrees. So going positively 330 could be going negatively 30, or if you were to spin around a few times, negative 7. Landing in the exact same spot. Wait, how do you know it would land in the exact same spot? What did you guys have to think about with negative 750? Yeah, every full circle is a 360, right? So negative 360, another 360 would be negative 720, and then how much more did you have to go? Another negative 30. Boop, 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 boop. Huh? Yeah, exactly. Robbie was going for it. You guys can check 32 as I answer Kyle's question. Negative 30? Oh, thank you. Hypo. No, I appreciate it. That's exactly what I need your guys' participation for. Do you guys all agree this should have been negative 135? Yeah. What quadrant? Yeah, because it needs to go negative 90 and negative 45 more. Dun, 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 dun. Dun, dun. All better. All better. Okay, sorry, number 32. Good. If you get the answer wrong, remember, double check the question really quickly, as Kyle just demonstrated for us, because the question was wrong. The answer key was wrong. It happens every now and then. 32 was easy. It was in degrees. So 90 minus 180 minus. Oh, letter B, not possible. Yeah, remember, it has to be less than in order to have something to add up to. To add up to positively to get to the angle. So no complement, supplement is 87 for letter B. 38 got fun. You were building bridges, right? Now, as you built bridges for these two, the pi's ended up canceling because there were pi's already in the answer, in the beginning representation of the angle. So the pi's canceled. 12 into 180 ended up being 15. 7 15s is 105. The pi's canceled. 3 goes into 180 is 60. There were 7 60s, if you think about slices. Although it's way easier in radians, but there were 7 60s or 7 pi over 3s. Anyway, going in the negative direction, negative 420. Number 44 also had a pi, so it turned out to be kind of nice, except 8 doesn't go into 180 evenly. Uh-oh, is something wrong? What's wrong? Ah, party poopers. Not you, the book. Okay. Was it positive or negative? Positive. 5 pi over 4? But still, what bridge did you guys multiply by? So the degrees ended up pi, but also the understood radian label that's never written. Okay, cool. And we end up with 4 goes into 180 45 times. Ooh, does that make sense? 180 pi cut into fourths or 45s. Maybe radians make more sense But anyway, 4 into 18 is 4. 4 into 20 is 5. So 545s. Oh, 545s. Oh, that ends up being so much easier to do radians and say it's 1 1/4 calzone. Just saying. But you do end up with 5 and 2, 225 degrees. Okay, but 44 is okay? Are we disagreeing with 44 too? Okay. 52, you were plugging and chugging to your to your formula, but you can't plug and chug the degree. You had to change it to radians first because, as we said in our notes, all of these formulas need radians. Gavin, what's up?
Do we have to round to
Oh, I see it. No, I always prefer 3. So if your answer would round to be that, just check it. You're good. Yeah, because you could have done something like 7.849. I just made that up, but it could have been like a 84 something. For number 76, it was talking about like the proportionality of different variables with arc length, which is S, and radius. So 76 is more of a relationship problem. And so it says arc length. What's
76 is a degree or radian, like where you
Oh! We actually talked about that one in class.
Yeah.
Nice. So forget that. Blah, 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 blah. The long story short is, who's bigger? A degree? Ding. Or a radius wrapped around? Oh, a radian's way bigger. And more specific, isn't a radian about 60 degrees, approximately? Approximately. Okay, are we done? Ugh. That was nasty. Pause. Before we totally transition, do you guys have anything that you want to ask me? Evens or odds on 4.1, Kyle?
I'll do it
44.
Yeah, I just like math wrong.
What was the bridge that you multiplied by?
180 over pi. 180 degrees.
Pi is reduced, so do the understood radian label. 8 goes into, now, here's the struggle. 8 goes into 180, not evenly. You could try a B2 and then 2 and then So instead, I would pull out, does a 4 go in? A 4 2 and 4 goes into 18 4 times, carry the 2, 4 goes into 25 times. So you could do 15 45s, which would be 10 45s. 15 times 45 is equal to 10 times 45 plus 5 times 45, which would be, we already figured out 225, right? So that ends up being 675 all over 2, which ends up 2 into 6 is 3, 2 into 17 is 8, 2 into 15 is 7? Point, and then do we have like a 5 after that? Something like that?
Yeah.
Did I do it too fast?
But yeah, it's
What would it end up being? Did I do my math wrong?
37. What's that much?
Oh, 37?
337.
Oh, 337. What did I do wrong? 3. Oh, I said 17. 2 goes into 6 evenly. 3. Just kidding. And then 2 goes into 7 3 times. And then 15 is 7, then 0.5. Is that better? Got it. Silly math. Anything else? 52. Was that one of the formula ones? Okay, so in the formula ones, you have to attach it to a formula. And just a quick heads up, guys, for the test, I know that we're a long way out from chapter 4 test, but for the test, the point of this chapter is not these like arc length formulas. If this was a physics class, a geometry class, yeah, we'd probably be testing on that, but it's not. We're just showing you some applications where radians are necessary, kind of like section 3.5, where we saw all these different problems where logarithms and exponentials were necessary, you might see later. Same thing here, but we're just seeing, can you do the math? So find the length of the arc. That makes me think right away of the variable s equals, and there's a formula for that, r theta, on a circle of radius r intercepted by a central angle theta. Oh, I think this is the right formula. And so for number, Tony, you said 52, right? For number 52, it literally is a plug and chug. The only problem is when we go to plug in for all of the formulas in physics that need angles, without trig, having to do with arc length. Without trig, so no sines or cosines or tangents, we must have the angles in the notes we talked about, they must be in radians. If they're not in radians, it's not going to work because degrees have nothing to do with the actual length around. Radians do. Degrees don't. Degrees are just little rotation tick marks. So the problem is this formula is completely invalid unless I'm actually dealing with radians, which has to do with the distance around. And so when you go ahead and convert the 150, I'm pretty sure you're good now, but we would go ahead and build a bridge. Degrees on bottom, radians on top. 15 over 18 ends up being 5 pi over 6. So plug that in. Yeah. Anything else from 4.1 going once, twice, sold. I'm going in the book to section 4.2, but as I get that ready to go, let me go ahead and get you guys starting to grade 4.2. Rachel, quick warning. There are two versions. There's a version A and a version B. So that has to go with those ones. I'm going to scroll down because odd even should have been pretty quick for you guys to grade. Let me give you a second to keep on checking on number 6 and 18. So that freeze? Nope, there it goes. Enter. Okay. I have the book ready for questions once we get there. Yeah. Yes, you can. I think, remember, I'm trying to help you get more of a mastery on these topics so that you can go more mental math style. So in my mind, it's faster to say the twos will always reduce if it's on top of each other. But if you want to be multiplying by the reciprocal until you get in the habit and say, oh, hey, they always go away. It's legal. It's legal. It just takes a little longer. Robbie. Okay. Okay, thanks, bud. Hang on to that, though. Number 30, number 40. Number 30 is another, like, find all 6. There's going to be some undefineds, because as soon as you have a 0, anytime you have a 1 over 0, it's going to be undefined, or a number over 0. We're not talking about wholes or vertical asymptotes right now, even though we could kind of bring that discussion in, but for right now, whenever you have an over 0, undefined. Number 40 forced you to use the even and odd properties. You could have been so confused if you didn't look at the formulas that we wrote down yesterday regarding even and odd. Cosine of a negative always stays the same. Cosine is even. Cosine of a negative always stays the same. Secant might have been a little bit harder, but secant is just, if you guys looked at your formulas, cosine is x and secant is 1 over x. So the same way that cosine stays the same, secant's going to stay the same, because if he's 1 over cosine, then, well, the cosine stays the same. So it'd be 1 over negative 3/4, which flips to be negative 4/3. Secant is the reciprocal of cosine, which we saw in our formulas by cosine being x and secant being 1 over x. But you had to use that even odd property or else you would have been a little bit lost. Number 60. Did that one talk about like a random point in the middle of a quadrant that you were talking about? Is that right? No? I thought it was a random point in the middle of the quadrant. What number is that, 60? Yeah. It's a random point in the middle of a quadrant. If it's in the middle of a quadrant, is x or y 0? Well, if x or y aren't 0, is there going to be any problems to plugging into my formulas? Mm-mm. Which is why A says, just have a question on this year after year. That's why they all exist. They're all fine. Nobody's 0. It's in the middle of quadrant. Well, not the middle, literally, but it's in quadrant 3, not on an axis. And then when it was talking about letter B, whether they're positive or negative. Well, guys, before you figure out which trig functions are positive or negative, you have to think about whether x or y is positive or negative. And then in the third quadrant, what's the sign of both x and y? They're both negative. So anything that just has an x, cosine, it's negative. Secant, it's negative. Anything that just has a y, sine, it's negative. Cosecant, it's negative. Who's positive? Tangent and cotangent, because both of them have an x and a y, and a negative over a negative or a positive, a negative x over a negative y or a negative y over a negative x, both of the negatives will become positive. So in the third quadrant, who are the only trig functions that are going to be positive? Tangent and cotangent. All the rest are negative. Wait a minute. Is there a way of remembering, a trick to remembering, which trig functions are positive in which quadrants? Do you guys still have your patty papers? 4.2 questions in just a moment. Was that our last even? Go, team. Before we do question 4.2, which I have ready to go in case you guys have more, can you peek at your notes real fast in the unit circle? I think this is you guys. Yeah. Let's go to the unit circle really quick. Go find the patty paper, the one that you just taped in your notes. We're coming back to our homework unless you're like, I have no questions. Okay, then put it away. But if you do, just hold on. But unit circle, ¿dónde está? Aquí. If you have a different colored pen or highlighter, I would grab that out now. And I would put an A in the first quadrant, an S in the second quadrant, a T in the third quadrant, and a C in the fourth quadrant. Mr. Crawford used to teach it, all students take calculus. Okay, good. That way no one can just tune it out and say, I'm not taking calculus. Okay, all students take classes. Oh, go team. All right. All students take classes, all students take calculus, all students take chemistry anyways. What does it stand for? All means all, and that's all that all means. None of the other words really correspond besides letters. But all is nice because which trig functions are positive in the first quadrant? All x's are positive, all y's are positive. Think about your formulas. All the formulas are positive. Hence, all the trig, all 6, positive in the first quadrant. Second quadrant. This is for the people that need to memorize and aren't so much visual as far as like, oh, the x is negative, the y is positive. If you are more visual, you might not even need to think about these unless you're double checking your answer. But any angle in the second quadrant is going to have what being positive? Sine, and who is dependent on sine? If sine is y, who else only has a y? Cosecant, which is 1 over y. So sine and cosecant, sine and 1 over sine. So sine and 1 over sine are positive. Who's negative? Everybody else. Cosine and tangent and cotangent. If you ever, like on a quiz, a second quadrant angle, if it's supposed to be negative, hopefully it is. My visual people, my memorizing people, this might be the way that you memorize what kind to put on the number you need. Third quadrant, we just talked about that one. Tangent and his reciprocal, 1 over tangent. Tangent and 1 over tangent. Tangent and cotangent, positive. Everybody else negative. Fourth quadrant, cosine and 1 over cosine. Cosine and secant are positive because the x's are positive. Everybody else is negative. Quick reminder, because we didn't talk about it yesterday, because I wanted you guys to see the homework problem first. All students take calculus, ways of remembering the signs of all 6 trig functions in the quadrants. And with that, let's go ahead and go back to section 4.2 in case there's a question. I know Robbie. Let's start with yours. 27? 47. Aha, I like it. Get out your calculators. Unless you already learned how to use them last night. There are 2 times. Well, 2 main times. Yeah, there are 2 main times. It's hard to use your calculator with trig. Like just normal trig, like solving trig. Ooh, I need to put in my license, huh? I've been too lazy. I have to go find it in an email somewhere. Okay. There are 2 times trig gets hard in the calculator. One of them is with things like secant and cotangent. So when you have the reciprocal functions is what we'll eventually end up calling them. secant, cosecant, and cotangent, the ones that have 1 over, or the reciprocal of the original 3, sine, cosine, tangent. That can be hard. But what's even harder is when we have secant inverse, cosecant inverse, and cotangent inverse. That gets even harder. But for right now, we're just having to deal with how to put tangent. Wait, tangent is a button. Forget him. I'm just looking at all of them. Oh, cosecant. Cosine's easy. He has a button. Secant and cotangent. You have to build off of the formulas that you know. So if you look in your table, secant is 1 over x, which is cosine. The way I remember it with the reciprocal functions is the letters never go together, aka cosine goes with secant and sine goes with cosecant. So it's not SSCC, it's always 1S and 1C. I don't know, super silly, but it stuck with me since I first learned it. So I memorized, or I know the trick of secant can't go with sine. No 2 S's. So therefore secant goes with cosine, 1 over cosine. That's literally what you do. You do 1 over cosine. The only dilemma that could have also gotten the answer wrong for you is if you went to put in the 1 over 8 and you didn't double check what mode you were in. Because what goes into a trig function is an angle. And in all of those angles, 43 through 48, I don't see 1 degree mark. Do you? So since there's not 1 degree mark, am I supposed to be, and I actually don't know what I am I supposed to be in degrees? No, I need to be in radians. There are no degree marks on any of those angles, so I need to put in 1.8. I need my calculator to be in degree mode. Nope, radian mode. Hi. And then you'll have your correct answer of negative 4.401. Is that cool? Any other questions from homework? Tony? 18. What was going on in 18? Evaluate all 6. Okay, we'll go fast. Hopefully from last night, some of you guys have your table already memorized, because 18, you're doing all 6. And from this section, we're doing from 1 ordered pair. True?
Yeah. 18 is just a sign.
Oh, it's not all 6? I was ready to have fun.
We can do all.
That's all right. We'll do just 3. Okay, but how are we doing it in this chapter, in this section? The circle. And the circle says, you better figure out where he is, and I see 1 1/3 calzones. Yay! No, negative 1 1/3 calzones. Oh. So we go this direction, right? 1 full calzone, and then a third. I'm in the second quadrant. So I know that in the second quadrant, I'm going to go left, which means a negative x. I'm going to go up, which means a positive y. And if you guys realize that this is just at a third, at a pi over 3 in the second quadrant, or at 2 pi over 3. If you are visual, hopefully you can think left a little, 1/2, and then up a lot, aka root 3 over 2. If you're not visual, maybe you're starting to memorize the points and say, oh, at that location, it's just negative 1/2 root 3 over 2. Cool. But this has an x and a y, right? So we have x right, we have our y right here, and then we go ahead and say, who is sine? Oh, let's not do that. Okay. Sine of t, cosine of t, tangent of t. Sine is going to be the y. Cosine is going to be the x. Tangent, I always write it sine, then cosine, then tangent to build you up to the cheater chart. That is an option for remembering the unit circle. I always write sine, then cosine, because if sine is y and cosine is x and tangent is y over x, if I write the sine, then the cosine, to get the tangent, all I have to do is divide these two, right? So then I say root 3 over 2 over negative is reduced, and I end up with dun, 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 dun. How would I get all 6? Flip it and rationalize times root 3 over root 3. Flip it and, oh, nice, negative 2. That would be secant. And then cotangent. Flip it and then rationalize, which would be times root 3 over 3. So I'd have 2 root 3 over 3. I'd have negative 2, and I'd have negative root 3 over 3 for my cosecant, secant, cotangent. Tony, does that answer okay?
I don't know why is it like 1/3. Does it have like negative 1/3?
Oh, and the answers? Ooh, let me check out the word. 1/3. There's an over 3 to begin with, but that just says cut it into thirds. And then pi over 3, maybe this is what you're asking? Or pi over 3, isn't that -1 and 1/3 pi? So then we go negative pi and then 1/3. That makes sense? Oh. No. If you were doing, I mean, you could. So we'd still do all 6. Yeah. Good question. Anything else? Gavin. 60B. For those of you guys that are good and ready to go with homework, go ahead and, that's the one we just talked about. Go ahead and get out your notes and get ready to go with a pencil. For those of you guys that are done. 60B, this is the one that we talked about with signs. Signs as in positive or negative. So all the 6 that you were dealing with in homework, sine, cosine, tangent, cosecant, secant, cotangent. They were just asking positive or negative. So in the third quadrant, because they showed it in the third quadrant, we know x is negative and y is negative to get to any point there. So in your, I'm going to go to the notes, in your formulas, as far as how to get all the different trig functions with x's and y's, if x is negative and y is negative, sine is negative, x is negative, cosine is negative. A negative over a negative is a positive, tangent's positive. They were just asking for the positive or negative of each one based upon if x is negative and if y is negative. So, negative, negative, positive, negative, negative, positive. And that was the answer. Or you could just say, everybody's negative but tangent and cotangent who are positive. All right, section 4.3, I told you guys I'd show you triangles, and now is the time. What if I was to label this triangle with x and y and 1? Ooh. X and y and 1. Now hold on, let's relate this to how you've done this before. Not that you haven't seen the x and the y and the 1, but couldn't we also call this opposite? True. And this would be adjacent. And this would be hypotenuse. And when we're doing the opposites, don't we usually think about h and a? O, not 0. O. How do we find sine? So, cosine, ka. Tangent, oa. Soka toa. Which, going to x's and y's, wouldn't sine be opposite over hypotenuse, so y? Wouldn't cosine be adjacent over hypotenuse, so x? And wouldn't tangent be opposite over adjacent, so y over x? You guys agree? It's our table, and it's just SOHCAHTOA. But we're not done yet. Because cosecant, I know, Mr. Chase stole it. It used to be, it was introduced in pre. But it's a good thing to steal. HPrecalc used to be mine. Cosecant flips sine, aka CHO. Hypotenuse over opposite. Secant flips cosine. And cotangent flips OA to be ow. Adjacent over opposite. So SOHCAHTOA and HPrecalc. And HPrecalc. So what would cosecant be? Well, you could literally say hypotenuse over, say flip him, and well, y is y over 1. Secant, hypotenuse over adjacent, or flip him, the reciprocal of x would be 1 over x. And cotangent, adjacent over opposite, would be, it makes it memorable, x over y. I'm not sure why I'm doing some of my fractions with the little slanty ones and some of them with up and down. I apologize if that bugs you. Oh, now it's green. That's even worse. On paper, when I do it, it's like when the fraction gets too big and bulky to go up and down, I'm like, okay, fine. Ugh, and I squish it. So what you'll check out. But what do you notice? Your entire table that theoretically yesterday might have been like, oh, stink, I need to memorize it, all comes from geometry and a right triangle. So how do triangles relate to a circle? Before I answer that question, let's do a weird problem. Because this one says, find, it's not asking what happens, it's asking for the cosine and the tangent. So if we take the triangle that we just saw, we could say opposite over hypotenuse of somebody is 0.6, which would be 6/10, which would be 3/5. True? The ratio, if we were to make this decimal into a ratio, 6/10 is 3/5. So if I have an opposite, or at least a representation of the opposite, and if I have a representation of the hypotenuse, isn't cosine just asking for adjacent over hypotenuse, and tangent's asking for opposite over adjacent? Hey, I have H. Hey, I have O, but I don't have... But if just remember a triangle, isn't a right triangle something that if I know two sides, I can solve for the third? So couldn't I plug in a 3 and plug in a 5 for some arbitrary theta? And then know from geometry, oh, it's a 4. So now here's the struggle. When we go to fill in cosine of theta, we're going to hypotenuse. And for tangent of theta, we're going to say opposite over adjacent and be done. But we have to keep our wits about us. Talking about trig angles, this is only assuming that the triangle, where did I draw it? In the first quadrant. Triangles? There are triangles in the circle? What if I was to, I know I'm trying to find it. Where is it? Donde está? It's over here. Are we not putting it in the circle at all? Oh, that's no fun. That's okay. You can write down the formulas. Eventually, maybe after homework, I'll show you where the triangles show up in the circle. Actually, you guys write that, and I'll have fun up here showing you where the triangles show up in the circle. Keep going, keep going. No, wrong way. I kind of draw a representation of what we just saw in the unit circle by scaling everybody back and not going over 4 and up 3. But saying he needs to fit into 1, so I can make it 5/5. That way, 1, which is the radius, corresponds to the 5 and the 4 and the 3. I can scale any triangle back to be in the unit circle. And this one doesn't hit at a pi over 6 or a pi over 4 or a pi over 3, because these are not the same numbers that we were dealing with in our ordered pairs, but it does actually still hit the circle. Just going to hit the circle somewhere in between my nice ones that we memorize. And we can actually break the entire unit circle down to really 2 triangles, a 45-45 and a 30-60. And that is where the 1/2 and the √3/2 come from. That we'll see another day. For right now, though, instead, we're just taking the table that you guys already talked about. We're taking the table that you guys already talked about, where sine was x. Sorry, where sine was y. And saying, hey, instead of saying 1 over y, let's say 1 over sine. It's actually a lot better because the ordered pairs aren't necessarily what we want you to take away from trigonometry. We want you to be able to deal with the functions themselves. So instead of saying cosecant is 1 over y, we can say cosecant is 1 over sine. And similarly, it's a little awkward, but we can actually technically say sine is 1 over cosecant. I actually want you guys, though, to put parentheses around, because we rarely make a nicer trig function, aka the 3 buttons on your calculator. We rarely make a nicer trig function one of the harder ones. We rarely go that direction. We're almost always using these ones if we're using reciprocal identities. Quotient identities. Whose tangent? Sine over cosine. Cotangent, cosine over sine. Y over x and x over y. And the cool thing is, from what I just showed you, if we can take any point on the unit circle, which used to be xy, and still technically is, and say, well, hold on, the cosine is the x and the sine is the y. If we can actually draw a triangle to that point, all of a sudden we can take the x of the triangle and say, hey, he's cosine. And the y of the triangle, hey, he's sine. And maybe you guys realize where these Pythagorean properties come from. Because it says, oh, take any cosine of an angle, square it. Take any sine of an angle, square it, add it, and you get 1. These other two are different manipulations, transformations, of the exact same one that I'll get to show you tomorrow. But quick heads up. Not only can you say sine squared plus cosine squared is 1, arrange all of these. Why am I telling you this? Remember how last chapter we learned all these fundamental things and used them to solve puzzles? We're doing the same thing this chapter, but with trig. We'll get there. Puzzles are coming. Bye, guys. See you later. This homework isn't due until Monday. I can't. Today's Thursday. Monday. Choir kids, make sure you get notes tomorrow. Try me.